Now we come to the boundary layer scaling. We defined the boundary layer, the region that is close to the solid boundary where the fluid is flowing and the viscous effects are felt. But away from that, the effects of the viscosity are negligible and can be ignored, and therefore the fluid is flowing as if there is no viscosity. It is not feeling the existence of any solid body. So the flow field could be divided into two parts. One, a closed region where viscous effects are there, known as boundary layer, and the other is a potential flow field where the viscous effects are not felt. And that depends on, as we mentioned, on the Reynolds number. Then we come to the scaling, as we mentioned, that how do we scale, how do we realize that what is the thickness of the boundary layer in a particular flow when we consider a particular specific problem, because things will change from problem to problem, different flow fields, different thickness or different conditions. So as it is normal, when we consider, let us say, two-dimensional Navier-Stokes equations of motion, steady equations of motion, then the variation with respect to time, that part will be dropped. And then if we will assume that fluid is flowing with a uniform velocity u away from the solid body, so u can be taken as a free stream velocity that is away from the body. Then the thickness of boundary layer is denoted by delta, and delta may vary. It may depend on x, but not on y, because we have mentioned that as we go away from the solid body, the effects of viscosity are reduced and can be ignored. Length, as always, the length of the solid body can be considered as a typical scaling unit and is denoted here by L in the direction of x-axis. So these are the few things which we shall consider for our scaling while considering the equations of motion. In a steady motion is du by dx plus dv by dy equal to 0 in a two-dimensional setup where we have already defined u is the x component of velocity and v is the component in the normal direction, that is in the y direction. So the term du, partial derivative of u with respect to partial derivative of x, it will scale as u over L, because the first part, this will have the same dimensions as that of u, and in the denominator we can observe that there is x appearing, and x we have taken to be in the x direction. The scaling parameter unit we have taken to be some standard length L that can be related to, let's say, the length of the solid body that is present in the flow field. And delta will be showing us the thickness of boundary layer. You can see it in the flow field with a red line that shows us. So if we try to measure and compute the scaling of these variables that are here, then du by dx is of the order of u over L, and similarly dv by dy is of the order of v over delta. In the y direction, the thickness is typical length scale is delta, which may be corresponding to the thickness of the boundary layer, and v is of course the velocity component in the y direction, and therefore the velocity component v will have the dimensions, they will be of the order of delta over L times u. So delta u by delta x is of the order of u over L. V, from this we derive that v is of the order of delta over L into U. And further, if delta over L is very small, because we are assuming that the thickness of the boundary layer tends to be very small, if we divide it by the length of the body at the typical scale, the ratio should be much smaller compared to 1, and therefore it's much more less than 1, and hence the ratio of V over U will be less than 1. Then similarly, we try to come and see how all these terms are come and continue, and what will be the dimensions of the pressure. Pressure here is being denoted by PD. PD refers to the dynamic pressure, the pressure that is there as the fluid is moving. So it is not stationary. If the fluid is not stationary, the fluid is moving, and therefore we are taking into consideration the dynamic pressure. Then, recalling from the Bernoulli's equation, we know that the pressure is of the order of rho into U square, and this is from the dimensional analysis that we were doing. And we have already seen in our last slide that the velocity component V is of the order of delta over L into U. So substituting these values into the equation of motion in the x direction, then we will have the dimensions of each component as shown here, U square over L. The second term will again be of the order of U square over L. So is this term referring to the dynamic pressure, and then the first part, this one, will be of the order of nu into U over L square. And lastly, since Y is being represented, is being reflected by the thickness of the boundary layer delta, so it will be of the order of nu U over delta square. And then these terms, as we have seen in our earlier slide, we want to normalize things. And for normalizing it, we want to divide it, sort of make it into 1, and we can see that if we try to divide each term by U square over L, or multiply each term by L over U square, then we will see we get the first term to be of order 1, so is the second term, so is this term. However, these two terms that are related to, that are the non-linear terms, and also that are related to the viscous effects, they will be of the order of nu over UL and L over delta square times nu over UL. We know the Reynolds number. Reynolds number RE is defined as U rho over mu, and the same thing could be written as U over mu over rho. And mu over rho, as you know, is nu. So therefore, we are trying to convert this nu and all these values in terms of Reynolds number. And Reynolds number, you can see, therefore can be shown here as U into L over nu. Now, we are interested in the flow field in two parts. One, where the viscous effects are so much that in a very narrow field, where we say that the boundary layer thickness is delta, and the other is away from it, where of course the Reynolds number will be large. But where the viscosity effect, then the Reynolds number there will not be so large.